In this video, we're going to cover everything you never wanted to know about statistics, at least the first part of it. We'll start out with a brief review of the research process, and then we'll get into building statistical models. Here are the objectives of this video. You can go ahead and pause the video if you want to watch all of this. And this is actually the list of the objectives for the next couple of videos. The broad perspective of the research process is what we have on the screen here. You see something that interests you, a phenomenon, and you come up with a question about why or how it might occur. Then you come up with an idea of an explanation of what happens. That's your theory. Why is it that this happens? And then based on that, you generate predictions on why it happens. That's where we start attaching measures and values to it that we can test. Then we go ahead and we test out our predictions. In order to do that, you collect data and then you analyze the data. The questions you're looking for there are, what are the outcomes of your analysis? Either your analysis supports your theory or your analysis goes against your theory and you have to modify it. Either way, you end up going through the process more to either build more support for your theory or do analysis on your modified theory. And the idea behind testing our hypothesis is that when we're testing our hypotheses, we are involving building statistical models of the phenomenon of interest. And why do we build statistical models? Think of it as an analogy of building a hospital. If we wanted to build a hospital, it would be foolish to just go out and start building. Instead, we look at other hospitals, we read about other hospitals, maybe collect data about our other hospitals being built to see what worked and what didn't work. Using what we learned, we would come up with an idea of what our hospital would look like. That's our model. We test our real model in a scaled down version instead of a full-sized hospital. Except for the model size, we try to get the model to fit reality as much as we can. And we can use our model to predict things about the reality. We can simulate, say, heavy winds, heavy loads, or anything else we'd like to using our model. So if this is what we want our hospital to look like in the real world, this is a pretty good fit. If this was our scaled down model, this would be a moderate fit, but this would be a poor fit for our testing purposes. So we want something that's as good a fit as we can make it. Scientists and researchers do pretty much the same thing, except that they build statistical models of real things to attempt to predict how certain phenomena occur under certain conditions. We usually don't have access to the real world situation when working in the social sciences, but we still want our models to be as accurate as possible, so our predictions are as accurate as possible. The statistical model we build must represent the data collected, in other words, the observed data, as closely as possible. Because we don't have access to the real world situation, we have to infer things based on the models we build. In other words, we might not have access to the entire population worth of data, so we take a sample and we use that to infer things based on the models we build. And the degree to which a statistical model represents the data collected is known as the fit of the model. And just as in our example here with the hospital model, we want a good fit. Since we're talking about populations and samples and all, let's review the differences between populations and samples. In the population, we're talking about everything, all possible observations of a set of people or objects of interest. And then the sample is a portion or a part of the population of interest. And we use that sample to infer something about the population. And what you want to do is think parameters. That'll come into play later, and think statistics when you're talking about sample. Population, parameter, sample, statistics. Now here we have the one and only model that you'll ever need in statistics. That may be a bit of an exaggeration, but the idea behind this is giving you an overview or an outline of what we're looking at when we're fitting our data. The equation just means that the real world data we observe can be predicted from the model we come up with and fit to the data, and then we have some amount of error. So we want the outcome. The outcome is equal to the model that we have, plus there's some type of error left over. So we observe some sort of real-world data, and then we try to fit our model to it, and then there's some error left over. And just so you understand, the little I in the subscript here just refers to the ith score. If we collected data on 3 people, we could replace that I with each of their names. And so we have here that model can be replaced by, could be a regression model, could be an ANOVA model, it could be some other type of statistical model, and then we have the error left over. In previous videos we've talked about the mean before, and that's a simple statistical model. Probably one of the simplest we'll use in statistics is the mean. Although it may seem odd thinking of the mean as a model, but it is a model because it represents a summary of the data. The mean is a hypothetical value that can be calculated for any data set. It doesn't have to be a value that's actually observed in the data set. For example, if we took 5 statistics lecturers and measured the number of friends that they had, we might find the following data: 1, 3, 4, 3, and 2. If we take the mean number of friends, this can be calculated by adding the values we obtained and dividing by the number of values measured. Now, we know that it's impossible to have 2.6 friends, which is what we would get if we added up 1, 3, 4, 3, 2 and divided it by 5. So we know it's impossible to have 2.6 friends. And so the mean value is a hypothetical value. As such, the mean is a model that we create to summarize our data. The important thing is that we can use the value of the mean computed in our sample to estimate the value in the population, which is the value we're really interested in finding out about. And we've talked about this formula before. It's nothing to get too afraid of or startled by or confused by. What we're doing is we're just adding up all of the observations that we have, and then we're dividing them by the number of observations we have. And if you wanted to read this summation formula here in the numerator, it's the sum of x sub I as, which is right here, as I goes from 1 to n. When we see this symbol later, we'll probably see it with just the summation symbol and then the x sub I. We won't see the n and then the I equals 1. It's easier to display it that way, but this is the way you may see it in some textbooks. Going back to our hospital analogy, we want to know how closely our hospital model resembles the real hospital that we want to build. With most statistical models, we can determine whether the model is accurate by looking at how different our real data are from the model that we created. For our example, let's say we observe that instructor 1 has 1 friend. Our model predicts the mean to be 2.6. Remember, the mean or the model includes the mean of all the instructors. The reality is that instructor 1 has 1 friend. So we would have a 1 in the outcome of instructor 1. Using algebra, we can solve for the error and determine that the error equals negative 1.26. So here we've put the 1 in place, and we know that our mean was 2.6 that we figured out, and we know that there's some error in there, and that error is associated with instructor 1. So with a little bit of algebra, so what we can find is that the error is 1 minus 2.6, or in other words, negative 1.6. And because the error is a negative number and represents the fact that it represents the fact that our model overestimates the lecturer's popularity. In other words, our model mean, the 2.6, is what our model predicts. So our model predicts that our instructor number 1 will have 2.6 friends, but he actually only has 1. So the deviance is the difference between what we observe and what we predict using our model. The mean is a model of what happens in the real world. It's the typical score. It's not a perfect representation of the data. How can we assess how well the mean represents the reality? Looking at it graphically, this is an example of a perfect fit, which normally doesn't occur, doesn't occur when we're dealing with people. Each instructor has 5 friends, so the average or the mean of our instructor's friends is also 5, which would mean that our model, the mean of 5 or the mean which equals 5, also represents reality for each of our instructors. Each instructor has 5 friends. Our model predicts the number of friends, in other words the mean, to be 5. As we saw on the previous slide, a deviation is the difference between the mean and the actual data point. Deviations can be calculated by taking each score and subtracting the mean, our model, from it. As we saw in the previous slide, a deviation is the difference between the mean and the actual data point. What do I actually mean when I say that? Let's look at an example of observations that are not perfectly fitted to the model. In this example, again, we have 5 instructors, but this time the model, in other words the mean, doesn't fit perfectly to the data. Our mean, which is the model, is 2.6 friends per instructor. That's indicated by the horizontal dark black line in the center. Instructor 1 only has 1 friend. He deviates from the model by -1.6 friends. Instructor 5, on the other hand, has 4 friends. Look at Instructor 5. So he or she has a deviation of 1.4. So we can look at the accuracy or fit of each of the instructors separately, but what if we want a fit of the entire model overall? Well, what if we added all the errors or the deviations? Would we get the fit then? No, because some of them are negative and some are positive, potentially offsetting each other, as was the case in our example right here. So what can we do to determine the overall fit? Well, we can square those errors to get rid of the negative numbers, and that leads to the sum of squared errors. So we take each score, subtract from it the mean to get our deviation. So we have this instructor had 1 friend, minus 2.6 gives us -1.6. Then we square that to get 2.56. And we do that for each of our instructors and the number of friends that they have. And as we discussed, if we added the deviations without squaring them, the deviations would cancel out because some are positive and some are negative. When we sum the squared deviations, however, we get the sum of squared errors, and we don't have the problem of them canceling each other out because they all are positive when you square them. So now that we have the sum of squared errors, we know that how good a fit the model is to the data, right? Well, not exactly. As we've said in the previous video, the sum of squared errors is affected by the amount of data we have. The more observations that we have, the higher the sum of squared errors. So we keep dumping in more and more friends or instructors and the amount of friends that they have, assuming they have any, and this number here, this total, will increase. To resolve the problem, though, we can take the average of the sum of squared errors and we get the mean squared error. I'm only going to stop on this for a moment because this is really not used very frequently. I think I've seen it once in an article, and it's just another measure of dispersion that we can do, and it's sort of a step along the way to the standard deviation and variance. So you can look at this if you'd like, but I'm going to continue on. Standard deviation tells us how well the mean represents the sample data. But if we're going to estimate, we want to estimate the parameter in the population. If we're going to do that, we need to know how well the sample mean represents the values in the population. Well, how do we do that? We start by looking at the sampling error. Since we are only taking a portion of the population when we sample, hence the term we sample from the population, it's unlikely that the sample mean will be exactly equal to the population mean. Same goes for standard deviation, variance, etc. The difference between a population parameter and the corresponding sample statistic is called the sampling error. So we could have a difference between the x bar, which is our sample mean, and the mu, which is our population mean or standard deviation, and the sigma, which is the sampling standard deviation and the population standard deviation, and the variance difference as well. And that's called the sampling error. And the sampling distribution of the sample mean, in other words, the sampling distribution, is a probability distribution consisting of all possible sample means of a given sample size selected from a population. If we organize the means of all possible samples into a probability distribution, the result is called the sampling distribution of the sample means. Let's see how we can just construct a sampling distribution of the sample mean with an example. So in this example, we have TARDIS Industries. They have 7 production employees, and that's considered the population. The hourly earnings of each employee are given in the table below. Now we're going to use just 7 employees because, as you'll see shortly, it gets pretty busy on the amount of calculations that we have to do. And here are the questions that we want to answer. What is the population mean? What is the sampling distribution of the sample mean for samples of size 2? What is the mean of the sampling distribution? What observations can be made about the population and the sampling distribution? Let's start answering these questions. So the first question that we had was, what does the population mean? Well, we happen to have the entire population here only because this is an example to show you the sampling distribution of the sample mean. In reality, we probably won't have the entire population to work with, but we do here. So we're going to go ahead and calculate the sample mean by adding up all of our values and dividing by the number of observations that we have. So we have 7 employees. We add up all of their hourly earnings and we divide by 7. And we get $7.71. Kind of make a mental note of the $7.71. The second thing we're going to do is we're going to determine the number of combinations of samples of 2. If you remember in our scenario here, that's what we're doing as the question for number 2. What's the sampling distribution of the sample mean for samples of size 2? And you're going to see later again how complex this gets, why we're only using 2 as our common number, why we need to select all possible samples of 2. And this formula here, don't bother memorizing it, but it's the combination formula. And we know that from that there are 21 possible samples by using this combination formula. I'll briefly go through the formula, but don't get too hung up about it. The large N is what refers to the number of observations that we have. In this case, the number of employees that we have. The small n is how many possible samples we're looking for without replacement. So that's the small n, and in this case it's 2. So all you do is you fill in those calculations, and if you remember from high school math, the exclamation point means n factorial. We calculate all of that out and we find that we have 21. Next, we determine the 21 sample means from all possible samples of 2 that can be drawn from the population. So these are every possible combination of 2 employees that we have with the 7 employees, and their corresponding hourly earnings. So if we took Joe and Sam, they each have hourly earnings of 7, which gives us a sum of 14 and a mean of 7, and so on down the list. These 21 sample means are used to construct a probability distribution. Here's our distribution. So the sample mean of 7 occurred 3 times, so the probability is 0.14 or 14.29%, and so on down the list for each of these. The next thing that we do is we determine the mean of the sampling distribution of the sample mean by summing the sample means and dividing by the number of samples. So we sum up all of the sample means and we divide it by the total number of samples, and we get $7.71. Remember I told you to make a mental note of the $7.71? The mean of all the sample means is usually written as mu sub x bar, and in this case it's $7.71, which indicates, or which is the same value as what we had in our population mean. So in other words, going through all of this calculation, what we've done is we've taken every possible combination of sampling size 2 of all of our employees, calculated out the mean, and found the sampling distribution of the sample mean, and we found that our mu sub x bar, remember the mu indicates that it's a population value because we have considered all possible samples, and then the sub x bar indicates that it's a sampling distribution of the sample mean, and we got $7.71, which is the same value as we had in the population. The whole point here is that the sampling distribution of the sample mean, if we took every possible combination of a sample size x, every possible combination, and we took the mean and we found that out, it would equate to the population mean. In reality, we won't have such an easy data set usually of 7 employees, but the principle remains the same, and we make decisions based off of that later on in our studies. So here are some observations that we can make on this, based on this example. The mean of the distribution of the sample mean that we got, $7.71, is equal to the mean of the population. And then we can also look, based on the pictures here, here was our population distribution, and here's the distribution of the sample mean. The spread in the distribution of the sample mean is less than the spread in the population values. And as size of the sample is increased, the spread of the distribution of the sample mean becomes smaller. So the more we have in our sample set, the more the less the spread of the data, or the lower value of the spread of the data. And then the shape of the sampling distribution of the sample mean, again over here, and the shape of the frequency distribution of the population values over here are different. The distribution of the sample mean tends to be more bell-shaped and to approximate the normal distribution. We'll also find out that as this gets larger, it gets even closer toward the bell-shaped curve and approximating the normal distribution. So letter B here provides a good segue into our discussion of the central limit theorem. And we've been talking about this already. Now this is just to clarify it. The central limit theorem states that if all samples of a particular size are selected from any population, the sampling distribution of the sample mean approximates a normal distribution, and that approximation improves with larger samples. So there are some further bullets as well. If the population follows a normal probability distribution, remember we're talking about the population. If the population is already normal, then any sample size, for any sample size, the sampling distribution of the sample mean will also be normal. So if our population is normal, our sampling distribution of the sample mean will be normal. If the population distribution is symmetrical but not normal, the normal shape of the distribution of the sample mean begins to emerge with samples as small as 10. And don't worry, we're going to show pictures a little bit further on, or the next slide. If a population distribution that is skewed or has thick tails, it may require samples of 30 or more to observe the normality feature. Again, we're talking about the population, but in many cases we don't know the population, so what we're doing with the central limit theorem is clarifying some points about it so that we can use that central limit theorem to estimate statistical inference about the population at a later point. Finally, the mean of the sampling distribution is equal to mu, and the variance is equal to the variance divided by n, also written as the sigma squared divided by n, or s squared divided by n. Now the point here is that if these are the population, the shaded areas up here are all our population. That's what the real population data is. But if this is an example of what we might see on if our population data is shaped like this, bimodal, and we take a sample of 2, it might look something like this, but then as we get to 6 or 30, it'll look closer to a normal distribution. Now granted, these normal distributions are a little bit leptokurtic. They're a little bit higher than what they would really be looking like, and it's just a matter, I think, of the image being squished a little bit on the screen. Now in the second distribution, it's a similar type of occurrence. You'll see that when we have a really low sample amount on each of these population distributions, we've sampled only 2 on each of these, you'll see that the distributions of the sampling distribution does not look all that normal. But as you increase the number of observations, or the number of samples that we have, that is, you approximate the normal distribution more. So, and that's regardless of the shape of the population distribution. The sample distributions converge on normal distribution shape regardless of the population distribution. Most statisticians consider a sample of 30 or more to be sufficiently large for the Central Limit Theorem to be used. On the next page, I'm going to show you a reference to an application and a video that should help you a little bit with understanding the Central Limit Theorem. The Rice Virtual Lab in Statistics here, if you click on this link, it'll take you to an application where you can change the population distribution, you can change the number of samples that you're going to do, and then animate it, and it'll do each of the samples that you want it to do and show you what it looks like on the sampling distribution of the sample means. Now in Khan Academy video, they go through this application and just apply it in the video and go into it with a little bit more discussion on the sampling distribution of the sample mean. We saw that the mean of the sampling distribution is the population mean. In other words, that is, the mu sub x bar equals mu. And that leads us to the standard deviation of the sampling distribution of the sampling mean, sometimes just called standard error. But again, it's the standard deviation of the sampling distribution of the sample mean. And if you understand the different terms that are in that longer definition, it might make it a little bit easier to understand what we're looking at. So if the mean of the sampling distribution is the population mean, that is mu sub x bar equals mu, and the standard deviation of the population is estimated by s, the standard deviation of the sample means, s, is divided by the square root of n, the number of observations in the sample. So here we have the formula. The standard error of the mean is equal to the population standard deviation divided by the square root of the number of observations in the sample. And all that was to tell us that the standard error is the standard deviation of sample means, and that it is a measure of how representative a sample is likely to be of the population. A large standard error relative to the sample mean means there is a lot of variability between the means of different samples. And so the sample we have might not be a very accurate representation of the population. A small standard error, small means that means that the sample means are similar to the population mean, and our sample is likely to be a good representation of the population. For now, we're going to complete the video so that we don't have our heads explode. I hope this was helpful to you, and I hope that you gained something from it. Have a great day.